What's up, all you badass mathematicians? So today we're going to continue on with limits, and we're going to look at a few examples where it's going to be really hard to figure out the graph of the function. So how can we figure out these limits without using the graph? So our first example here, limit as x approaches 5, x squared minus 25 over x minus 5. So first thing I would at least try would be to plug in this value for the function. So when I plug in 25 minus 25 over 5 minus 5, so we end up getting 0 over 0. So let's say f of 5 leads to 0 over 0. So whenever you end up with a 0 in the denominator, or a form like 0 over 0 or infinity over infinity, this should always indicate do more work. Do more work. It's not enough information to figure out anything from this value. So maybe some questions you have are, okay, a 0 is in the numerator, so maybe overall this should be 0. Or you're dividing a number by itself, so maybe it should be 1. Or you're dividing by 0, so it should be undefined. So if you end up with this form, this is called an indeterminate form, then you should always realize that you need to do more work, because we don't know how quickly our numerator is approaching 0 versus our denominator is approaching 0. So this is really telling us that our limit can actually be anything. We don't have enough information quite yet. So let's continue on. So we're going to tackle this problem algebraically. So the limit as x approaches 5 of x squared minus 25. So this can be rewritten as x plus 5, x minus 5. Whenever you factor, it's good to get in a habit of multiplying through again and making sure you get back what you started with. So x times x is x squared plus 5x minus 5x, and then minus 25. So you end up with x squared minus 25. And then this is going to be divided by x minus 5. So these now cancel out. So limit as x approaches 5 of x plus 5 is equal to 10. So for this problem, it's important to first recognize that when you plug in directly, you end up with this indeterminate form. So this should indicate to you that you don't have enough information and need to do more work. So here we opt to simplify algebraically, so we can end up in a simplified form, which we can then plug in our limit and get back our finite value. So in this case, our final answer is 10. Now let's move on to our next problem. So the limit as x approaches 7, x squared minus 49 times x plus 13 over x plus 7. Wow. Okay. So let's tackle this down, and let's use the same type of strategy from part A. So limit as x approaches 7 of x plus 7 times x minus 7 times x plus 13 all over x plus 7. So then this ends up giving us the limit as x approaches 7. These cancel out. So x minus 7 times x plus 13. So x minus 7, 7 minus 7. So this is going to then be equal to 7 minus 7 times 7 plus 13, which is going to equal 0. So we did all that work just to get 0. So something that's important to keep in mind here is that actually maybe it is a good idea to just start off by plugging in our value. It's really common to see these complicated examples, but in reality, you really only need to go through doing more work when you've actually reached a roadblock. So back in part A, our roadblock was that when we plugged in, we ended up getting 0 over 0. So this then gives the motivation for why we're doing this extra algebra, to get it down to a simple form. But here in part B, my mistake was I just jumped straight into the algebra, trying to simplify the form. Note that this is not incorrect. This is a perfectly valid way of trying to tackle this problem, and 0 is the correct answer. But something that, if you're lazy like me, you could try plugging in the 7 and seeing if you end up with this roadblock. So now maybe wait. Can we plug in directly? So now what if we do 7 squared minus 49 times 7 plus 13 all over 7 plus 7. So actually this is not an indeterminate form, and it's not even undefined because we don't have a 0 in the denominator. So evaluating this out, you're actually going to get a 0 in the numerator and a positive number in the denominator, meaning that this overall is going to be equal to 0. So in general, I think a good strategy is it's fine to plug in for the value, but you need to be aware when you actually need to do more work, and this value isn't going to give you the limit directly. So now to our final example. So here, limit as x approaches 5, x squared plus 25 over x minus 5. So let's try and plug in directly. So 5 squared plus 25 all over 5 minus 5. So we end up with a 0 in the denominator, so we should probably do more work. So maybe we try factoring. So x minus 5, x plus 5 all over x minus 5. Okay, so this is the same type of problem. Limit as x approaches 5, x plus 5 is equal to 10. So what's my issue here? I had a 0 in the denominator, which meant I needed to do more work. And now I factored this all out. So another common mistake is when you see a lot of these problems, everything starts looking similar, and blindly applying tools to a problem can often lead to simple mistakes. So here I need to realize that this numerator is actually x squared plus 25 instead of x squared minus 25 and x squared minus 49. So it's totally okay to have the hypothesis that this is going to factor into this, but it's always important to double check and make sure that it still multiplies through. So when you multiply this all through, you're actually going to get x squared minus 25, meaning this is not a valid way to factor this numerator. In fact, if you keep trying for a while, you'll realize that this numerator is actually in a simplified form, so there is no way to factor it. So the reason I included this example is when you see a lot of these problems, it's really easy to get into a habit of applying specifically one tool. So from part A to part B, you might be tempted to just do the factoring algebra, when in fact that wasn't even necessary. And now comparing part C, you might go into autopilot and do this factoring again, even though these numerators are not even equal. So it's important to be flexible in the tools you're using, and always try and double check your initial work, because it might be wrong. So in the case for part C, we're actually going to want to approach from the right and left to get a better idea. So the limit as x approaches 5 from the right, and the limit as x approaches 5 from the left. So the way I like to tackle these problems is using a table to get the general trend. So here are x values, and here are f of x. So we're interested in 5. So let's start with 5.1. So f of x is going to be 5.1 squared plus 25 all over 0.1. So now 5.1 is too large, so we need to keep getting closer to 5 from the right side. So now this becomes 5.01 squared plus 25 all over 0.01. And then we can keep going. 5.001 5.001 squared plus 25 all divided by 0.001. Sorry, this is getting a little bit hard to read. The important thing here to notice is that our numerator is changing, but it's not actually changing that much. The numerators for all of these are going to be approximately 50. And our numerator, in fact, is approaching 50 as we approach 5. So our numerator is approaching 50. And what is our denominator approaching? Our denominator is approaching 0. So what happens when you have a positive number and you keep dividing it by a smaller and smaller number? So you can imagine now we're talking about a number really close to 50 in the numerator divided by 0.000000001, and you can keep on expanding this to smaller and smaller values, closer and closer to 5. So this should get you into the idea that from the right, our limit is actually uncapped. So we say it's approaching infinity. And from the left, since the only thing that's changing is our x value here, so x squared, regardless of whether it's positive or negative, is still going to be the same. So our numerator will be approaching 50. And now for the denominator, we're approaching from the left. So let's do this out. So let's say we have negative 5.1. Then we have negative 5.1 squared plus 25 all over negative 0.1. Sorry about this. This number shouldn't be negative at all. This is a mistake right here. Alright, so let's get back to red. So we're approaching it from the right. Negative 5.1 is way far away from 5. So we're actually looking at 4.9. 4.9. So 4.9 squared plus 25, all divided by 4.9 minus 5, which is going to be our negative 0.1. So then what happens when we keep approaching from the left? So 4.99, getting even closer to 5. So 4.99 squared plus 25 all over negative 4.99 minus 5 is 0.01. So we can see that the numerator is still approaching our 50, regardless of whether we approach it from the right or left. So as we keep getting closer and closer to 5, our numerator is going to be getting closer and closer to 50. And now our denominator is getting closer and closer to 0, but from the left side. So I encourage you all to try and work these values out in your calculator. And what you'll hopefully see is that when we approach from the left, it's actually growing uncapped in the negative direction. So that means from the left, we're actually approaching negative infinity. So limit of f of x from the right is equal to infinity. Limit of f of x as x approaches 5 from the left is equal to negative infinity. So because we don't even agree on our direction here, we would then conclude that this limit does not exist. So maybe I'll do a separate video illustrating why we aren't saying infinity here, but instead we're saying does not exist. Because when we approach from the right, our limit is growing uncapped in the positive direction, meaning it's infinity. But when we're approaching from the left, it's minus infinity. So because these disagree, you're going to end up, if you were to graph this around 5, you're going to end up with some sort of behavior where approaching from the left, it's going like that, while approaching from the right, our behavior we expect to be something like this. So this is another aspect of why limits are helpful, because I had no idea anything about what a graph of this would look like, but by figuring out these limits, I'm able to figure out some amount of information. So as we can see here, we don't even agree in the direction. So we don't even have to be specific and say it's infinity, but rather we just flat out say this does not exist. All right, so I'll wrap it up there. Maybe I'll do a follow-up video on this problem because the work kind of got a little messy. Yeah, as always, if you have any questions or comments, please, I would appreciate that feedback, and have a good day. Thank you.